Okay, so continuing section 6.5, we're going to take a look at scientific notation here. What it's all about is dealing with large or small numbers in a more manageable way. And what we're doing here is we're taking a look at this number right here, which has lots of places, and we're going to move it so that it's just 5 point, the rest of the number, times 10 to a power. Here, if we actually count it up, we'd see that there's 12 moves as we move to the left from this decimal point here. If I move it over, I would count and actually see that there's 12 spaces as I move. You can actually see there's a group of 3, 2, 3, 4, 4 groups of 3, which is 12. So you can see that I moved it all the way right here and raised it to the 12th power. And if I multiplied it by 10 to the 12th power on my calculator, it would actually bring me back to this number right here. Okay, and we can also take numbers like this one and count up how far we need to move it to get to right there, and it actually moves. If I count all the little places, all the little zeros, it would actually be 19 spaces. Now the reason why it's negative is because this was a really small number to begin with, and I'm moving it to be 1.6, and we want the negative to represent that I moved it in a negative direction. And the strange thing is that you didn't move it in a negative direction, you actually moved it in a positive direction as far as right versus left goes. But the negative direction means that once it's here, I would want to move it towards the negative on the number line to make it go back to the number that it was originally. And up here it was positive because to make it the right number I want to move to the positive direction to make it what it was originally. Okay, so scientific notation is defined, it has to be, the A value is between 1 and 10. So it can't be 10, it has to be between 1 and 10, and n is any integers. So we're going to talk about some problems here and changing them around a little bit. What I want to identify is that these are close but not actually scientific. Here the decimal point is not behind the first number and in front of anything else. So what we'd have to do to move it is we'd have to go over one more place, which would actually take this number, which is positive right now, and because I moved it to the left, I want to add one more to make this 1.436 times 10 to the 4th power, which means that I'd have to move it one more place this direction to make it back to the original number that it was. Here we've got 0.634 times 10 to the 8th, and I need to move it back one space. And so what I'd end up doing is multiplying it by 7, or raising it to the 7th power, in other words, taking 1 away, or decreasing the 10's exponent by 1 to make this 6.34 times 10 to the 7th power, because from this place right now we're saying I got to go back 8 spots to make it the original number, and now we're saying, well, I already moved back one place, so now I just have to move it 7 more places back to make it the original number of what this was before it was written the way that it is. Okay, so here's the actual, if you want to follow some directions, I'm not going to read through these directions for you, but if you want to screenshot that and look at them and follow some directions, there they are for scientific notation. But here's some problems for us. We've got the length of Manhattan Island is approximately 708,660 inches. Not that we'd ever really go measure Manhattan with inches, but there it is. So what we can do is rewrite it in scientific notation, because this is awful to look at such a large number. And so to play with those numbers, we like them to be smaller. So what we want to do is find the decimal, which is at the end, and we move it over 1, 2, 3, 4, 5 places to be behind the 7. So we rewrite this to be 7.0866, and then whenever there's a 0 at the end, you don't write it. So we're not actually writing the 0. Say times 10 to the, how many places was it? 1, 2, 3, 4, 5 places to the 5th place power. Okay, and that is Manhattan in inches written in scientific notation. So the MacBook Air, it takes a very small part of a second to perform an operation. So we want to rewrite this to be in a more manageable number. Bottom line, we want to say 3.4 times 10 to some power. So we got to move that and make it happen. 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So we say negative 9 places is what we want to do to say that in scientific notation. Okay, so here we've got numbers that are in scientific notation. We want to make them back in standard notation. And as I said, the negative means that it was originally a small number. We have to move it to the negative direction to make it what it was. Down here, I've got a negative. That means I'm going to move to the negative direction. Here I have a positive. That means I'm going to move to the positive direction. So I move this 1, 2, 3, 4, 5, 6, 7 places. No, it didn't go all the way to the end. That's because originally the decimal was right there. So the precise length of a year is that many seconds, so I say 31556925.511. Not that you can see the last one, sorry, but there it is. And then over here we have the 2.0 times 10 to the negative 10. We write it point right there, and we move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. And what I need to do with these little holes is I need to put zeros back in there. And so this is how small the diameter of an atom is in regards to meters. Okay, so that's how we deal with scientific notation. We also need to do division and multiplication with scientific notation. So what we want to do here is look at when I have something in scientific notation, we're dividing by something else in scientific notation, the math comes out really nice. What we need to do is we need to divide the decimal part on its own, and we need to actually divide the tens on its own. So basically what we want to do is look at the fact that this can be done on our calculator, and then the rules for exponents say that we can take the 13 and the 8 and just subtract them. That's how we deal with our exponent rules. So we do this on our calculator, we do this using our exponent rules, and that's going to give us 10 to the 5th. And then we just have to finish by doing that on our calculator, which looks like I did right here. So sorry, we have 4.92 is what this actually would give us. And so now where this number came from, if I actually divide this on my calculator, what this comes from is my 0.4917, which actually rounds to 2. And so that number is rounded right there. So this is what my calculator gave me, and then what I need to do with it is take it and actually put it back in scientific notation, so that I get this 4.92 times 10 to the negative 1 if I moved it over one place. And so this part came from my calculator. This I moved so that it is in scientific notation now. And so that way, when I finally write my answer here, I'm actually just going to add the negative 1 and the 5 to the 10 to make my answer be in scientific notation. So the process is you divide the tens and reduce them the way that we did to the 10 to the 4th. We divide this part on my calculator, and then I have to actually work it back into scientific notation, and that gives me the front decimal, this 4.92, and then any moves that I had to make, I needed to deal with that at my final 10 to the 5th, take the 1 away from it, and that gives me my 10 to the 4th. Okay, so let's try and see how it works on my multiplication. So my multiplication, I do the same process I actually do with my numbers, my 2 times 3.4, separate from my 10 multiplication. So I actually say times 10 to the 24 or 27 minus 10. And so that way I can do this part and get 10 to the 17th. And then I actually multiply 2 times 3.4 on my calculator. So if I do that, I get 2 times 3.4, and it's going to give me 6.8. And this one's not going to need to do any rearranging, so that this is going to end up being my final answer here. So I multiply the numbers and the exponents, deal with them each separately. Okay. You're going to have a problem like this in your homework where you're having to analyze a graph. It says use the graphs to calculate the amount of national debt owed by each person in a country in 1990. Express answers in scientific notation. And so if I do that, I need to figure out in 1990 how much debt there was. So if I go over here and look at the red, I see this 5227, and I have to realize that this is in billions of dollars. And so the answer is 5.227 billion in exponential form. And so what we're saying is that this has 9 zeros after it, so that's where this part's coming from. We've got 5.227 times 10 to the 9th. And that's not actually in scientific notation. We need to fix that a little bit, but we'll come back to it in a moment. We've got rewriting 201 million in exponential form, and what that's looking at is our population in 1990. So we've got two numbers that we care about, and that's the 1990 here and the 1990 over here. So see the 2.1 here and see the 5.227 over there. Nothing else actually matters in this problem. So your job is to figure out what is the national debt by person. So we need to take our actual debt and divide it by population. So our job is to divide this number by this number. Now it would be a little bit more helpful if these were both in scientific notation. See if I did that on my computer. I didn't. That's right. So if I wrote it the way that it is, so this is debt divided by population. And so if I actually move this 1, 2, 3 places, I would add 3 places to this one. So this is actually 5.227 times 10 to the 9 plus 3 is 12 over, move this one over 2 places, 1, 2, and I get 2.01 times 10 to the 8. So that way it allows me to do division like I did earlier, where I divide these numbers here first. And so if I divide 5.227, so 5.227 divided by 2.01, that's going to give me 2.600, and I'll just round it there. So 2.6 like that times 10 to the, divide my tens, or subtract the tens actually. So it's really to the 12 minus 8 power. So my final answer is 2.6 times 10 to the 4th power there. So this is how much money a person actually owes per household in 1990. So if I actually, or per person, sorry, if I actually look at that in real dollars, that 4 means that I moved it over 4 places. So it's 2.6 moved over 1, 2, 3, 4 places. So that means per person, the national debt is $26,000 in 1990. Obviously, we owe much more per person now. And we're not talking about like debt that we have in our house. It's talking about national debt. So this is the portion of debt that you owe as far as the national government is concerned for how much it owes if we're actually to pay it off. And if they walked around and say, hey, everybody just pay off our debt, this is how much we would have had to done in 1990. Of course, it's much more now. That's not reassuring. So good luck with your lesson. If you have any questions, please email me with the Ask My Instructor feature of the lab.